Hi folks, in this video we're going to do an introduction to vector spaces. Now, vector spaces are one of the topics in linear algebra that is traditionally a little bit tougher, more challenging for students to learn. It certainly was for me. I had to see vector spaces in probably 2 or 3 math classes, and then it wasn't until I was in grad school TAing it that it like all just clicked and cemented in place. So I'm telling you this not to scare you or terrify you, but just to kind of, give you some comfort if you're like, oh, I just like, it's just there, and I'm just not getting it. That's a normal thing to happen, right? I don't know why it's like floating up here, but that's how I think of it. It's like this cloud that's floating, and I just can't reach. Or like you hold it for a second, but it's a cloud and it like dissipates. So that's okay. We're going to be working through this a lot. And the purpose of this video is to help give us something to hold on to when we are trying to grab at that wispy cloud in the videos to come. So in this video, we're going to do sort of like a vector space alphabet, I guess. These are not formal definitions at all. They are kind of big picture ideas of what we're going to be looking at. So it's an introduction to some of the jargon that we're going to see, and yeah, just kind of giving us something to hold on to so that we're still able to see the forest once we get into the trees of the details of our definitions, of our mathy definitions in the future. So let me pull up my list of the alphabet here, and yeah, we'll go through it. So it's our little alphabet in Microsoft Word. So V is for vector space, of course, because that's what this whole unit's going to be about. So when we think about what is a vector space is just a collection of objects that we can add and that we can multiply by a real number. So we're going to call those objects vectors. We're going to call that addition, and we're going to call that multiplication by a real number scalar multiplication. Now, vectors needn't be what you know vectors to be from calculus. So we don't need to have that I, J, K stuff going on, because our vectors don't necessarily have to be arrows in arrows in three-dimensional space. They could be matrices. They could be differentiable functions. They could be really any type of object, as long as it meets particular criteria. Similarly with addition, it doesn't have to be the traditional definition of addition for these objects, but we're going to call it addition. This is one of the challenges of generalizing something that we are so familiar with in a concrete space. So we're so familiar with vectors in R3, and we're accustomed to the things we can do with them. We're accustomed to how to add, vectors in R3, how to dot product them, how to cross product, all of those fun things. And it's not that none of that applies here. All of it applies, but we're going to be thinking bigger and broader than that small space. So don't let these words limit your imagination for what we can do with vector spaces. So when you're getting like a little like lost and afraid and scared in the woods, just remember a vector space is a collection of objects. You can do something called add them, and you can do something called scalar multiplication with them. Now, once you have your objects or your vectors, there are some things that we're going to do with them. And so that's why C is for linear combination. This is a linear algebra class, so we're going to see a lot of linear stuff for our definitions here. A linear combination is basically, if I give you 2 vectors or 1 vector or 2 vectors or more, what can you make out of them? So in this case, can you write one object in terms of one or more of your other objects using your operations? If you can, then that object is a linear combination of those others. So for example, suppose I have a Lego bricks, right? And I've got a 2x2 Lego brick, and I've got a 3x2 Lego brick. So if I take those two, I can get a 2x5 Lego brick. So that 2x5 Lego brick is a linear combination of the 2x2 and the 2x3. So that would be like the linear combination. If I have 2 objects, what object can I create out of them? S is for span. So span, the span of a set is all of the linear combinations you can make. So if I give you like a bag of 3 or 4 different kinds of Legos, but infinitely many of each type of Lego. So you have infinitely many 2x3 Legos at your disposal, for instance. And I say, okay, using all these different types of Legos, what other Legos can you build out of them? That's the span of the set. So yeah, so linear combination is, can you make it out of other objects in your set? And the span is every possible thing that you can create based off of the objects that you have. D is for linear dependence. So if you have a linearly dependent set, what that means basically is like one of your Lego pieces is redundant. So if I gave you a bag of Legos, right, classifications. So you have your 2x3 Legos, maybe you have a 2x2 Lego, and then let's say I gave you a 4x4 Lego. Well, that 4x4 Lego is redundant because I could just take 4 of my 2x2s and use them to create a 4x4. So that would be a linearly dependent set. I don't need to have the 4x4 there because I can create it out of the 2x2s. So that's a linearly dependent set. You have your collection of vectors, but one of the vectors can be created out of some of the other vectors in your set. So linear independence is if you can't do that. If every vector in your set is unique and necessary in some way, because you cannot make it out of the other objects in your set. So this is important because linear independence is going to be important for our B is for basis. So the basis of a set is what I think about what is the bare minimum generating set that I need for my vector space. That's going to be my basis. So the basis is, it's a collection of linearly independent vectors whose span is going to create the whole space. In other words, like if I were to give you, if I were to give you a 2x2 Lego, I can't, just using adding, I'm going to hold off on scalar multiplication because I don't want to break my Lego pieces. So I don't want like half a Lego piece. So if I gave you a 2x2 Lego, that doesn't generate all possible Legos because there's no way I could get a 2x3 unless I, destroyed the object that I had, which I'm not allowing in this hypothetical basic situation that we're thinking about. So, so that 2x2 Lego would not be a basis for all Legos. But if I had a 1x1 Lego, that would be the basis for all Legos, because then I could create any block out of that. Out of, however many combinations of the 1x1s. So the basis is like your essential generating set. You don't have any redundancies in it. Now, I have another word that begins with S, but we already used S before. So this is for like your $5 footlong. So this is your $5 sub space. So F is for subspace. A subspace is like a mini vector space that's contained in your big vector space. So for example, maybe in my Lego universe here, the vector space is all of those like brick Legos, but I could maybe have a subspace even by even. So like it's got 2x2s, it's got 4x2s, it's got 8x8s, but it doesn't have any odd things in it. And maybe in this world, I can create any even dimensional Lego out of the other even Legos. So that would be, everything would be kind of hunky-dory and safe in that universe. So that would be like a mini vector space in the big vector space. So that would be a subspace. Now P is for inner product. So we have a product there. And an inner product is a way of like multiplying vectors so that you get a scalar. So we have scalar multiplication. That's one of our operations on a vector space, where we take a scalar, we multiply it by a vector, and we get some sort of vector. The inner product is going to be where we take two vectors, multiply them, and get a scalar value. So it's kind of like, I think of it as like kind of bringing us down a dimension or so. So if you want to think of an inner product, you already know that's the dot product. So when you take the dot product of two vectors, you end up with a scalar value. So we're going to see what could be an inner product for some of those other kinds of vector spaces that we mentioned. And lastly, N is for norm. I always think of Cheers when I talk about norm, but the norm is like the size of your object in your vector space. So you can think of it as your magnitude, or in R3, right, it's like the length of the vector. So our norm is going to be the size or the magnitude of an object in our vector space. Okay, so I think that's it for our basic introduction to these. I know that that was a lot of information at once, but hopefully this video will serve as a useful reference so that when you're doing work and you're like, okay, what does span mean again? This at least gives you something to hold onto and kind of ground you in, oh, right, the span is just everything we can get. So that helps. I find that has helped me, and it's helped my students to kind of put pieces together once we get lost in the weeds. So in our next video, we're going to start digging in with some actual mathematical precise definitions. And our first definition is going to take a full page. So just make sure you're ready for that. Yeah, I'll see you then. Bye.